Okay, ji, Bismillahirrahmanirrahim. So, this is basically the last topic of this chapter, which is about searching, which is about searching. And we have studied two categories of searching. The first one is uninformed searches, and then now the second one is informed searches. And in informed searches, we have seen the greedy best first search as a first algorithm, and now we are seeing the second algorithm, which is about A star search. The idea of this A star search is to avoid those parts which are expensive. Expensive, expensive has a different meaning. Expensive in terms of time and expensive in terms of space, etc. In BFS, we have seen that we expended many irrelevant states, and same is the case with depth first search in uninformed searches. And then in greedy best first search, we have seen that there were, for example, if we want to go from Arad to Bukharas, as you can see on the slides, then there are different paths. One, this one is the second one, this last third one, and this fourth one, and even this fifth one. So these multiple paths is basically, you can say there are some parts in these multiple paths which are expensive, and there is a path which is an optimal path, and that is this one, going from Arad to Sibiu, Rimni Kubilsia, Patisti, and then Bukharas. This is the best one. So the rest of the paths are basically the expensive one. So this is the idea, to avoid expensive paths. And for this reason, in informed searches or heuristic searches, we come up with an idea of heuristic function. And in greedy best first search, we have seen a heuristic function that is something HSLD. And now in A star search, we are going to see another heuristic function. We can call it evaluation function also. And this evaluation function is equal to f of n is equal to g of n plus h of n. Here, g of n is basically the actual cost, and h of n is basically the heuristic cost, you can say. In previous example of greedy best first search, our heuristic function was this straight line distance function, and the table of straight line distance values were this. But here, h of n is similar to that straight line distance function, and the table that we will use is again the same. On the other hand, g of n is basically this cost, which is you are seeing on the map. This is the actual cost between different nodes here and here, which is written on the map. So now g of n is cost so far to reach a node or a state n, and h of n is estimated cost to goal from n. So idea is basically this one. For example, from Arad, you are going from Arad to Bukharas, and if you have reached from Arad to Sibiu, then this is the actual cost. And after Sibiu, if this is the path, then there are actual costs g of n, but we have to go through this node n to this Bukharest, which is a goal node. So we must have to include its heuristic cost, that is h of n, and that is something estimated cost, and the h of n is written here. So we have to consider both this actual cost in the map and the straight line distance values here. And this heuristic function, or this heuristic measure, f of n is equal to g of n plus h of n, is which we use in A star search, and this is an admissible algorithm or admissible heuristic function. This straight line distance function is admissible, which means acceptable, and it is already proved. And we know that straight line distance between any starting node and the end node, if I will clear, this is our starting node and this is our end node, then straight line function is something like to draw a straight line between the initial node and the destination node. And we know that this straight line distance is always the minimum shortest path, but it is not on the map. This straight line is not has an existence over this map, but if it has, then it would be the minimum shortest path. That's why we normally say that straight line distance HSLD never overestimates the actual road distance. So this would be the minimum, but in reality, the actual distance between different spots or locations would be greater than this straight line distance, and it would not be less than this straight SLD. So now its execution is basically given here on this slide. If we have to go from Arad to Bucharest according to this map, and by using this HSLD values, which is our h of n, and the values here on this map are g of n, then from Arad, according to the map, from Arad we have three possibilities: Srind, Sibiu, and Timisoara. And the g of n of Srind from Arad to Srind is 75, from Arad to Sibiu is 140, and from Arad to Timisoara is 118. This is g of n. And what is h of n? We can see that the h of n of Srind is this value, 374. The h of n of Sibiu is 253. H of n of Timisoara is 329. So now, according to this function, we have to add up these values, and then we have to decide that what is the minimum, and then by selecting that minimum, we have to process the algorithm. This is called A star search. So from Arad, I have three options: Sibiu, Timisoara, and Srind. The g of n of Sibiu is 140 from Arad to Sibiu. From Arad to Sibiu, the g of n is 140. And the h of n of Sibiu, is, from this table, is 253. So 140 plus 253 is 393. And similarly, from Arad to Timisoara, you can write the values like this one. And from Arad to Srind, you can write the values like this one. It is the summation of g of n plus h of n. And then now you have expanded the locations which are expendable from this initial node Arad. And now you have to select the minimum. What is the minimum? 393 is the minimum, because this is 447, this is 449. So 393 is the minimum. Now you have to select this one. And then you have to expand this Sibiu. After And now you can say from this CPU you have these parts, 4 parts, 1, 2, 3, and 4. From CPU you can go back to Arad. From CPU you can go to Oradi. From CPU you can go to Fagaras and then to Rimniku-Vilsia. So these 4 options are mentioned here. And if from CPU, if you go to Arad again, for example, from Arad to CPU is 140. And now you are going back again to Arad. So it is again 140 plus 140 in backward direction. So 140 plus 140 is equal to 280. So you can see 280 here. And then the value of Arad, h of n of Arad, h of n of Arad is 366. So you have to add up that value 366 and then you will get the summation 464. And similarly, you can do this with Fagaras, Oradi, and in Rimniku-Vilsia. And now you can say this is 6, you can see 646, 415, 671, 413, 447, and 449. So this is something the smallest. So now in the next execution, you have to select this Rimniku-Vilsia with the value 430. So from Rimniku-Vilsia, we have 1, 2, and 3 options, which is Sibiu, Battisti, and Craiova. So this is the expansion. And you can also write the values like f of n is equal to g of n plus h of n. And now from these all values, which are encircled, not this one, not this one, not this one, these outline circles. So what is the minimum in these outline circles? The minimum is Fagaras. So you have to select next and you have to expand it next in the next level. So that's why the expansion is, you can see here. And in this way, after that expansion, the next is the term of Battisti, which is the minimum. And then you can expand this Battisti. And from Battisti, you will get the goal node, that is the Bucharest. And it is something, 418 is the G of n. 418 is the G of n. From Arad to Sibiu, then Rimniku-Vilsia, then Battisti, and then Bucharest. If you add up the values here, from 140 plus 80, it is something 220, and then plus 97 plus 101. So you have to add up these costs, and this is G of n. And that G of n is 418, and then the H of n of Bucharest is 0. So that is, you can see here, 418 plus 0 is equal to 418. And then the algorithm will check that either it is a goal node, yes, it is a goal node, and then the algorithm will exit. This goal check is at the generation of every node in the algorithm. We will see when we will execute this algorithm. However, the execution of the A star search is very much clear now. Now, this is the algorithm. And for this algorithm, I will execute this algorithm on the board so that you can understand the things clearly. And I will also use this picture. So I am also starting the video. I don't know, either you will, oh sorry, the light is off. Okay, Ji. So this is the pseudo code or the algorithm for a star search, and you have to keep the map of Romania, this one, and the SLD in your mind. Though I will visit this screen again and again during my processing. Anyhow, so the first statement is saying that put node start, and our starting node is Arab, and we want to reach at Bukharas. Our destination node is Bukharas. So now put node start in the open list. So in this algorithm, we have two lists. One is the open list, and the other is the closed list. Open list is to represent the frontier, and the closed list is to represent the explored set that you already have seen in previous lectures. So put the node start in the open list with f of node start is equal to h of node start. Here h of node start means the heuristic value, the straight line distance value of that node from the table. You have to put that value as a heuristic function value, f of, because our equation is f of n is equal to g of n plus h of n, but here the equation is uh, not written in full because fully is not needed at this moment. So you will put starting node is Arad, you will put Arad in the open list. So now I am going to enable the video also so that you can see. I will take the help of this whiteboard also. So what I am going to say, I am writing the open list, and I am putting this Arad A. I am putting this A in the open list with f of node start, which is Arad, and then h of node start. So Arad, the value of h, the value of Arad in the straight line table. Here the value of Arad is 366. So I have to use that value. So my f of n. So here 366 will become the f of n of this Arad. Now, if you are seeing on the list, then after that at line number 2, it's a while loop while the open list is not empty. My open list, you can see we have one uh, state which is Arad in it. So it is not empty. So this loop will go on. This loop will go on until this will be empty. Then, so the open list is not empty, as you can see here. And then take, what you have to do, you have to take from the open list the node, current node. You have to take out this current node with the lowest. And what is that lowest? This formula. This is the lowest. You have to, this is f of n is equal to g of n plus h of n, the whole formula. So g of n of Arad is 0, because I have to start from here and I have to reach at here, and this is the g of n here. So at Arad, I didn't travel anything yet. So the g of n actual cost is 0. So 0 plus h of current node Arad. The h of current node Arad is 366. So 0 plus 366. So f of Arad is 366, as you can see here. 0 plus 366. It is 366 as you can see here on this slide. Okay, now move on. If Arad is a goal node, no, it is not. If it will be, then we reached on the goal node and we have to break, we have to exit, we have to make an exit from this algorithm. So the next statement is, so this condition is not true, so I will come on to the next statement, which is generate each state a node successor node. So I have to produce all successor nodes of the current node. So what are the successors? So the successors are Srind, I can go to Sibiu, and I can go to Timisoara. Three successors of Arad are you can see on this map. So as you can also see from this tree, there are three successors: Sibiu, Timisoara, and Srind. So now you have generated those three successors, and then you have a loop which is operating on these successors. So now you have to take one by one these successors, and then you have to execute this loop. So now I am taking first the CPU. You can take any, but I am taking the CPU so as to make an alignment with this algorithm for your easy understanding. So my successor is now, node successor is now my CPU. So then set successor current cost. So now I am going to set the current cost of this CPU, G of n, G of CPU, sorry. So node current, what is my current node? My current node is Arad actually. I can also, from these previous statements, my current node is, you can also write here, my current node is Arad. So, and my successor node successors are Sibiu, Timisoara, and Srind. Okay. So now I am executing for this one, for Sibiu. For Sibiu of current node is Arad. So the G of n of current node, G of n of Arad, G of n of Arad is 0. Actual cost of Arad is 0. So it is 0. Plus weight from Arad to CBU, which you can see on the map. Weight from Arad to CBU is 140. So you can add up this 140. You can add up this 140 with this 0, and you will get your current cost for the successor. So the current cost of successor's current cost. So my successor is CPU, this one. So the current cost is 140. I am writing it here. Okay, and then you will check node successor, which is CPU. CPU is on the open list. I don't have any CPU here in this open list. So, okay, this condition is false, then I will come here at else if. CPU is in the closed list. I don't have any closed list, so you can make a closed list also. You can make a, maybe here, you can make a closed list here. So closed list is empty at the moment. So I don't have anything in this closed list. Okay, then this condition is false, and then I will go to this else. Here in this else on the screen, it is written add this successor to open list. So I have to add CBU to open list. So this CBU, I have to add it here. Add it and set h of successor to be the heuristic distance to the node goal. So now you have to look into the table of SLD and you have to find the value for the CBU. So, okay, here the value of CBU is 253. So value of CBU is 253. I am writing it here at the top of this CBU just to remember it, and so that in next moments I will not do any mistake. So 253 is the heuristic cost, and now set G actual cost by setting the current cost of successor. Current cost of successor is 140. So current successor's current cost that you have calculated. So 140 that you have to fix as a. So I can write 140 here as a current cost that we already calculated here in this step at line number 8, which was the 180, 0 plus 140, like this. And then set the parent of the node successor to node current. And then you can set that what is the parent of this successor. The parent of this successor is this one. I can represent with an arrow. But before that, I can write these values, this heuristic value here, 253. It was not in the open list, it was not in the closed list, and then you added the successor CBU in the open list. And then you set the heuristic cost, and then you set the current cost, which is G of n. And then finally you set the parent of that successor, which is this one, which is Arad. And now this else is, this for loop is ended, not the else. This for loop is ended. When for loop is ended, now you will go back again to this for loop and you will deal the next successor. And what is that next successor? Next successor is Timisoara. So then again you have to set the cost. I am now clearing it. Timisoara. So the current cost or the actual cost of current node, that is 0. This current node is still Arad. So that's why it is 0. And then from this Arad to Timisoara, what is the cost? Arad to Timisoara? Arad to Timisoara is 118. So 0 plus 118, so I will have the cost 118, which I can write here. Okay, and then this successor is in the open list. This Timisoara is in the open list. No, it is not in the open list. Is it in the closed list? No, it is not in the closed list. Then here on else portion, add this successor to open list. So now I can write CL here. I need some space here. And maybe I can rewrite this whole thing. $140 253. And this is the parent. This was the previous step. This was the previous step. And now this Timisoara is not in the open list, not in the closed list. So what I have to do, I have to add, according to this algorithm, I have to add this successor to open list. So now I'm going to add this T here. After adding, I have to set the heuristic value, heuristic cost, and then I have to set the actual cost, which is successor's current cost, and then I have to set the parentage. I have to set that this successor belongs to which parent. So these three steps that I have to do. So heuristic value of Timisoara is, I can see here on this table, which is, which is 329. 329. So I can write it here, 329, at the top of this ladder. And then I have to, then else portion is ended, and then I have to set the current cost. Current cost is already calculated, which is 118 here. So I can rewrite 118 here. This is the setting of this current cost, execution of this statement. And then I have to set the parent. Who is the parent? The parent is again the same, Arad. And now the for loop is ended, and I have to go back again to this for loop. And what was the left? What is left? Only surrender is left. So set the current cost. It is again 0. Current node is Arad. So the actual cost of Arad is 0. 0 plus weight from Arad to surrender, which you can see on the map. From Arad to surrender, it is 75. So 0 plus 75 is equal to 75. So this is the current cost, 75. And then, is it in the open list? Surrender? No. Is it in the closed list? No. So I have to again go to this else portion on the algorithm. I can also make this screen a little bit bigger so that you will see these values. So is this successor, I have set the value as a 75 as a current cost, and then I am checking that this surrender is in the open list, no. In the closed list, no. So I have to execute this else portion. I have to add this into the open list, then I have to set the heuristic cost, and then I have to set the actual cost, and then I have to add the parentage. So set the heuristic. So I have to look over the table, and I have to see what is the value for surrender. It is 374. 374. 374. And actual cost is 75. By the way, I have to add this successor in the open list first at line 15. So I have to add it here, and then I have to set the heuristic cost 374 here and actual cost 75 here by using this line number 18 statement. And then I have set the parentage, which is again this one. Now all the successors of this Arad are evaluated. And now this for loop will be ended. For loop on the screen will be ended. And then I will come up to this line number 21, And now what I have to do, I have to add this current node. Current node is what? Current node is RR. This one, the parent. I have to add this current node to the closed list. So I have to add this RR here. Okay, and now the while loop is ended, and then I have to go back to this while loop. And here, while the open list is not empty, so open list is empty? No, open list is not empty. We have elements here. So it means that the loop will remain continued. And then again, I have to take something, some state from this open list, which has the minimum cost. Minimum cost by adding these two. This is my G of n, this is my H of n. G of n, H of n, G of n, H of n. So you have to add up these values, and then you will find that this CBU, this has the minimum value. CBU this has the greater value, but you have to add these values first. You have to add these values here, you have to add these values here. And then among these, you will find this one, CBU, with the lowest value. As you can see here, 140 plus 253. You can check it, 140, 253. The next is, it is 393. Next is 118, 329. 118, 329. And it is 447. And then 75 and 374. And it is 449. So this is something, the minimum. This is something, the minimum. Now, so you have to take the minimum from this open list by seeing their f of n. And what is the meaning of f of n? F of n is equal to g of n plus h of n. G of n plus h of n. G of n plus h of n. So this is the minimum. So I will take this out. It is up to you. You can take this out. And when you will take this out, this open list and closed list statements given in the algorithm, they will handle it. So then after taking it out, what you will take, I will take this CBU. And now you are checking, now your current node, f of this, your current node is now what? My current node is now CBU. And then you are checking this current node is goal node. No, it is not goal. Goal is Bukharas. So then you will generate all the successors of that node. And what are the successors of that node? You will see on this map. There are 4 successors: Arad, Oradi, Fagaras, and Rimni Kubilsia. 4 successors with their actual cost. So after generation of successors, you will execute this for loop again, which will execute on the number of successors. So there are 4 successors. So this loop will execute 4 times. My current node is what now? My current node is now CBU. So for the first time, I am going to take Arad as a successor of this CBU. So then G of n of current node, G of n of CBU is now 140 according to the map from Arad to CBU. G of n is 140. Here you can see from Arad to CBU, you have reached from Arad to CBU, and so the actual cost of CBU is now 140. And weight from CBU to node successor. So successor is what? Arad. From CBU to Arad, what is the weight? From CBU to Arad, again, what is the weight? It is again 140. So 140 plus 140. So 140 plus 140, you will get 280 as a current cost. Current cost of successor, Arad. So I am going to write the successors here. What are the successors? Arad, Oradi, Fagaras, and then maybe Rimnikudusia. So the current cost of successor that we have seen is now 280, not 140, not 0. Okay, because now you have traveled. Now you have traveled from Arad to CBO, and now CBO is the current node, not the Arad. And now from CBU to backward in Arad, you are calculating. So that's why it is 280 is the actual cost. Now you are checking. In previous step, you have taken out this node Arad from from this open list. So that's why in previous step, I forgot to mention, but in previous step, you have taken this out. When you were calculating f of n is equal to g of n plus h of n. Now you are checking that now my successor is Arad again. And now you are checking Arad is in open list. It is not, it is crossed. Arad in, then you are checking Arad in closed list. Yes, it is in closed list. When it is in closed list, then condition is true, and then you have to check if actual cost of Arad. Actual cost of Arad is what? It is 0. Actual cost. Okay, actual cost, G of n. And successor current cost, Arad current cost, what you have calculated? 280. So 0 less than or equal to 280. If condition is true, continue to line 20. So I have to continue to line 20. Line 20 is this one, which is the end of this for loop. So this Arad, you already started from Arad, and this Arad is coming as a repeated state. So in previous algorithms or in previous lectures and we have seen that how we can remove the repeated state, because this is something a loopy path. So how we can remove these loopy paths? Through graph search. And this is basically the mechanism of that graph search, that if there would be a repeated state, then there would be some mechanism in your algorithm to avoid those repeated states. And now we are avoiding. So this Arad is coming again as a repeated state, as a loopy path. So we are avoiding, we are ignoring these states. So that's why you are not calculating anything, and you are going to the end of this for loop. And at the end, at line 20, you have a closing braces for this for loop, which means that you have to go again to this for loop. And then you have to consider the next success. So we are leaving this Arad as it is, and we are moving toward this next successor. Next successor is over D. And then you have to calculate. Now you have to calculate the actual cost and the weight of the Oradi. What is the actual cost of Oradi? Let's see. From CBU to Oradi. Okay, from CBU to Oradi. What is the actual cost? What is the cost? 151. 151. And we are considering this one. And weight from current node, which is current node is CBU to successor node, which is ORAD to, so weight from CBU to ORAD is basically 151. This one, which I have highlighted, from CBU to, from CBU to ORAD, it is 151. And actual cost of current node. CBU, what is the actual cost of CBU? You have calculated already here in the previous step, 140. So 140 plus 151, it is 192 something. If it is 151, 140, 151. So 291. So the successor current cost is 291. 291. So this is current cost. And now you are going to check that this ORAD is in the open list. No, it is not. In the closed list, no, it is not. In the closed list, no, it is not. So then you will come up here at the else portion and you have to add this successor to the open list. So you have to add this ORAD. Maybe you are not seeing here, but maybe I have this option. So I have added, and then heuristic cost of ORAD. Heuristic cost of ORAD is 380. 380. And then current cost that you have calculated 291. Current cost you have calculated 291. And then setting the parentage. Parent, who is parent? Parent is CBU. Okay, and then loop is ended and you will go again to process the next successor. Next successor is Fagaras. Fagaras. Actual cost of current node. Current node is, node current is CBU, CBU. Actual cost is 140. So 140 plus weight from CBU to Fagaras. Weight from CBU to Fagaras is 99. So 99. And you have 9239. 239. Okay. So then 239 is basically the actual cost. You have set it for the Fagaras. And after that you are checking Fagaras is in open list? No. In closed list? No. Then again on the else portion, you have to add this to the open list. So I don't have a space. So what I am doing, I am writing this CLA here, and then so this is my, so I am writing this Fagaras here. Now you have to set the heuristic cost. Heuristic cost for Fagaras is 176. 176, and the current cost is 293. And then you have to set the parentage. Parentage is easy. So parentage is this one. And then you go back again to see the next successor. Next successor is RV. So you have to, and actual cost of current node, which is CBU, is 140. So 140 plus weight from CBU to RV, Rimni-Kovalevskaya. So weight from Sibiu to Rimni-Kovalevskaya is 80. So 320 is the actual cost. 320 is the successor current cost, which you can write it here for the moment, and we will use this value later on. Now you are checking this RV is in the open list, no. In the closed list, no. So again, on the else portion, I have to add this successor to the open list. So I am writing this RV here. And when I am considering this CPU, I have to again cut it out. Initially, not here. So now RV, set its heuristic cost. Heuristic cost of RV from the table is 193. 193, and the actual cost is 320. Set the parentage. Parentage is easy here. And now all the successors are finished. So this for loop will be finished. And now I will be here at this line 21. And I have to add current node. What is my current node? CPU. So I have to add this CPU into the closed list. So here you have to add CPU here. This closed list is behaving like explored set. And now only for checking, look at this, look at this. So after expansion of CPU, you have this RR, but we calculated some value and then we avoided this path because it is a loopy path. From CPU to Fagaras, it is 293 and 171. Fagaras, 293, 171. ORAD 291, ORAD 291 and 380. And similarly, Rimni-Kovalevskaya is 220, 193, 220, sorry. 140 and 80. 220, not 320. This is our mistake. 140 or and 8, 220. So now again, now again, I have added this CPU into the closed list, and now this while loop is ended, and you have to go back here, and then you have to check open list is empty. It is not, because only 2 current nodes are expanded yet. And these are the generated nodes, and these are in the open list, and these cancelled are in the closed list, which is for explored set, and this is for the frontier. This concept we are already seen in previous lectures. So open list is not empty. Not empty, then what I have to do? I have to select the minimum f of n. I have to select the state with minimum f of n from these existing ones. And if you will add up these things, which your algorithm will automatically do, what is the minimum? The next minimum, which is coming here, is Rimni-Kovalevskaya, which is 2 with 4, 17. So Fagaras is 215, ORAD, and all these nodes. Rimni-Kovalevskaya is basically the minimum. This one is going to be selected for the next step by adding this. And after selecting this, you have to check that it is a goal node. RV is not a goal node. Then you have to generate the successors, and what are their successors? Now look over this tree. Maybe it will shorten my time. You will expand these Craiova, Patisti, and Sibiu Again, this CPU is a repeated node, so our algorithm will evaluate some of its value and then it will ignore this value. So Krayevov and Petisti will be the successor nodes. And then you will check again what are the minimum in the next. Then this Fagaras 2 with 415 is the minimum and it will be expanded. This is basically, okay, I will let you know in a moment. Fagaras will be expanded. And after that, Petisti will be expanded here. And then from Patisti, you will reach at Bucharest, 418 is 418 plus 0. And here, these filled circles are basically in the closed list. And rest of the outlined circled states are in open list. And in this way, you can go on with this algorithm. And I hope that you will now do this thing by yourself, as it is not a difficult thing. The last statement is saying that if current node not equal to goal node, if you will process the whole tree, and if your current node, whatever it is not equal to the goal node, then exit. Then it means you have found nothing. You have not found your destination. So then it will exit with error that the open list is empty, and your open list will be empty and you will not reach at your destination. So now I am going to the next slide, and I hope that you will execute this algorithm by yourself. So now we will discuss some of its properties, and we are discussing 4 properties of every algorithm in this chapter. We are seeing their completeness, time complexity, space complexity, and optimality. So from the execution of this algorithm, you will see that it will always find the minimum. And it is also ignoring the loopy paths, which means it is also ignoring the infinite state spaces. So by considering these 2 options, definitely it will reach to a solution if that solution will exist in this whole space. So that's why we are saying that yes, it is complete. And if there are infinitely many nodes, if the state space is infinite, then definitely it will not end up if your solution is in greater depths. And if it is infinite, then it might be possible that there might be some loopy paths. And if there is loopy paths, you will not get your solution. So that's why you are saying that you will not get your solution. But here in this algorithm, we have seen that we are tackling the loopy paths here in open list and closed list mechanism. And closed list is for explored sets and open list is for the frontier. And by using these 2 lists and some instructions here, statements here, we are handling the loopy paths. We are basically handling the infinite state spaces. So that's why we are saying that it is complete. Yes, if there is a solution in the state space, you will get your solution with guarantee. So that's why it is complete. And when some algorithm is complete, then most of the time it is also optimal. And in this algorithm, we have a heuristic function f of n is equal to g of n plus h of n, which works by finding the state with the minimum cost, actually, minimum cost. So for example, if you look over this diagram, and this is basically the destination Bucharest with value 418, cumulative cost f of n. And then you will see, sorry, and then you can see that this Patisti, the previous one, this Patisti has a value 417. This Patisti is coming from this RV, and this RV has the value in previous step. What is that step? 413, which is again less than 418. Fagaras is also less than 418. CBU is also less than 418. So what I want to say that it is optimal, but with some conditions. This A star algorithm expands all nodes whose f of n would be less than the cost of the optimal solution. So the optimal solution C star is 418. So if you will check the expanded nodes before expanded nodes, these filled circles are basically expanded nodes. If you will check these nodes, you will see that their value would be either equal or less than this 418. This condition is written here. F of n either would be less than C star, either it would be equal to C star. And A star will not expand any node with f of n greater than C star. It will not expand those nodes. There are nodes here with 615 and 607 and 591, but these are not expanded. These are in the open list. These are on the frontier. Expanded are what ones? Expanded are these ones which are in filled circles, which are in the closed list. So optimal is yes. Time complexity order of B, which is B is the number of branches, branching factor basically. And epsilon m is the maximum depth of the state space. So again, this algorithm is executing different states by seeing their cost actually. And we don't know in which direction it will go. It will not behave like depth first search, selecting state from the left and going towards the depths. No. And even it will not behave like BFS, like for example, level by level opening of the states. No. We don't know actually the direction in this algorithm because it will execute according to the costs of the states, and those costs are using some heuristic function, and that is f of n is equal to g of n plus h of n. So what we have to do, we can say that it will go up to the maximum depth of the state space. That's why this m is here, but we are mentioning this epsilon here. And what is that epsilon? Epsilon is basically the relative error that either our heuristic function is good or not. So epsilon is h star minus h divided by h star. And h star is what? H star is optimal heuristic. And h is what? It is your normal h of n that you are using here. This is h of n. The heuristic that you are following is h of n. But if your heuristic is not up to the optimal heuristic, and we are representing that heuristic function with h star, then you have to calculate some error between these two heuristic functions or heuristic measures. So if this is the equation, and if in your if in this equation, if your h is 0, if your heuristic function that you are following in any algorithm, if this But we are talking about this A star. So, okay, let's talk about this A star. If your heuristic function in this A star is 0, which means it is not working, its value is 0, it is not working, then you can put this value 0 here, and then it would become H star over H star, and you will get epsilon as a 1. And then it means that your relative error is at the highest peak, is 100%, you can say. And if it is the case, if your heuristic function is absent, if your heuristic measure is not working properly, it is absent, then this A star would behave like uniform cost search that you have already seen in the category of uninformed search strategies. But if your heuristic search, if your heuristic measure is working like an optimal heuristic, measure, H is equal to H star, then it is perfect, and then you can say that your uh, heuristic measure is really working, because now it is not equal to 0. Now it is H star, and H star minus H star is equal to something, anyhow, 0 by H star. And you are not getting 1 here, because it is the equation of relative error. How much error you are seeing. If the value of this error is 1, that means you are experiencing 100% relative error. But if it is 0, then it means that there is no error in your equation. So that's why it is order of B raised power m, but with a relative error epsilon, which depends on your heuristic function. And the space is no doubt order of Bm. B is the branching factor of the tree, and M is the maximum depth of the tree. So all nodes in that space, that state space that your algorithm will generate, it will keep it in memory. So that's why it is order of B raised power M. There are issues in this algorithm, in this search. First, we don't know at how much depth it will go, because it is executing by the cost. It will go up to the maximum depth of the state space, or it will end up even in the beginning, depends on your input. But in reality, normally it goes up to the maximum level of depth. So when it will go up to the maximum level of depth, then it is an impractical algorithm. Why we're saying because its time complexity is exponential, B exponent m. So the exponential complexity of this algorithm with respect to the depth of the node, which is m, makes this algorithm impractical in finding an optimal solution. By the way, it will find the solution, but due to depth we are seeing this statement. And basically, its computation time is not the actual issue. Issue is that when it will execute, it will generate so many nodes that the memory of your computation device will end before the generation, before the computation time. Your memory will be ended first. So that is basically the real issue. So that's why this A star search algorithm is not practical for large scale problem. For small scale like this one, for an assignment, it's okay. But for large projects, it is not feasible. There are some topics that you have to study by yourself from the topic from the book. These topics are memory bounded heuristic searches, the next topic after this one. And then there are some theoretical stuff in a few paragraphs, learning to search better, and then heuristic functions. There are some additional information about heuristic function that you have to read by yourself from the textbook that we are following. And this is the lab work number 3. You have to go onto these URLs, and then you have to download the source code. You have to configure it on your machines. and then you have to submit the reports accordingly. Thank you very much. See you next time, inshallah.